Okay, hi everybody. So in previous problems, we saw derivatives of maps like this, where the input was one-dimensional. And there, the derivative of this map was the velocity of a curve, right? This corresponded to a curve in some higher dimensional space, and the derivative was a velocity vector. Okay, but now we're going to do something new. What if the input space is higher dimensional? So before, the input space was just R1, but now, if it's higher dimensions, there are more directions to move, okay? So the derivative of a map like this with a higher dimensional input, and now we'll take the output to be one-dimensional we'll get there eventually, where both are higher dimensional, but for now, well then we can move in different directions, in the input space. And we'll always start at some point in the input space. Then what is the derivative? Well, the derivative is this limit. H here is a real number, and it's going to just shrink. The only purpose of h is to shrink to 0, so we can get instantaneous behavior at the point P. And again, we'll do final minus initial. Now this time, because the output space is one-dimensional, then f of P plus hv will be a number. F of P will be a number. But P and V are vectors. P is a vector because the inputs are vectors. Okay, so anyway, what's the problem? Use this limit definition to show that this symbol applied to this formula gives this formula. So what does this mean? So first of all, I'll use my words first. Partial x, we say partial derivative, or partial derivative in the x direction. Partial x means we move in direction. So remember, there's going to be a direction v. So in direction, v equals 1, 0. Why? Because, well, we move in direction, let's say, the x dimension. We're just moving in the x dimension only, okay? And so when I look up here, looking at the formula, I see x and y. So that means my input space is two-dimensional. So that means that we have a map where the input space is two-dimensional, taking a point x comma y, because I just don't see any other variables in here. And I'm looking here. Okay, and then we're going to move in the x dimension. Good, because one of our variables is x. The other is y. We're not going to move in the y direction. But anyway, okay, so what's this map? Well, the output is one-dimensional, and so it's given by this formula right here. That's our map, okay? So looking at that formula, I see an x and y, so that means that f is our map. Okay, now let's draw a picture, okay? This is completely new, so I don't expect you to understand really what's going on, but you'll see by the end. So here we'll add some pictures. Our input space is R2, and we usually say that the horizontal direction is x and the vertical is y. You could switch it up, but that would be, then people are going to be confused by you. So it's just worthwhile to learn which one is which. And then we're going to start at a random point. So we're going to maybe start here. This is the point P equals x comma y. It's just one of the points. And so our formula will work for all points simultaneously. And then where are we going to move? Because remember, we need to move in some direction. But now we could move that way, we could move that way, we could move that way, we could go that way, we could move that way. Well, all those are more complicated. We will learn how to move in those directions later. But for now, we're just going to move purely along the x dimension. And that is the vector 1, 0, or 1, 0, or I hat, or E1, right? And vectors, we can move them around, so I like to visualize it up at the point where we're starting. Okay, so remember, we're finding the derivative of a map in direction v at the point P. At the point P in direction v. Okay, the derivative of f at the point P in the direction v means we do this. Okay, so let's draw it in a picture. So then my map f goes to, well, the output space is R1. R1. So there's my picture of R1. And somewhere is f of p plus a movement along the direction v, and somewhere else is f of p. And I'm just going to subtract those numbers. Okay, so I think that's basically my picture. The picture isn't helpful for a computer, it's just helpful for us to sort of imagine what these things are. So now we have to actually use this formula. Use the limit definition. This is a limit definition of a derivative. Okay? So, what do we do? Well, we've discovered that since we're taking partial x, that means that v is the simple vector down here. And so let's just plug into the formula. So I'm going to take this formula, and then actually it's worth just memorizing this formula. F of the point we're starting at, and then we're going to move. We're going to move some amount h is a real number, in the direction v. Okay? And then we're going to divide by that number h and take the limit as h goes to 0. Okay? And that is the derivative of the map f at the point P in the direction v. Okay? So really take your time to get this notation down. I would see people go df of p v, or just like they do all sorts of random things that is just not what we do. So this is what people write for the derivative at the point P in the direction v. Okay, our point P is x comma y. Our direction v is the simplest direction, 1 comma 0. How did I know that was the direction? That is what this symbol means. This symbol means move in that simple direction. Okay? Anyway, so let's apply this formula. We have our map f. And so we can do this. And we know what p is. P, so sort of over here I'll say, remember, p is x comma y. V is 1 comma 0. H is a real number. And that's everything here. The map f is this formula. So let's apply this. So f of, okay, p is, let's write our vectors vertically. X, y, plus some real number in the motion 1, 0, minus f of x, y. And then divide by h. Okay, so now let's just add these vectors. So right here, we're going to add these vectors. Well, x plus h, and then y plus 0. Pause for a moment. Do you see how I made this into this? Okay, and then this will just stay the same. Maybe at this point it's easier to write the sort of horizontally. And maybe you put extra parentheses. I don't really know. And I'm not really super concerned with that. What I do want is that when you plug into the formula, it is correct. So now we're going to replace, wherever we see an x, we're going to put an x plus h. So first of all, I mean, let's just do this one. That one's easy. We just copy this formula. Copy, paste. I mean, you have to write it again. Okay, that is f applied to the point xy. I'm going to subtract and then divide by this number h. And then what do I do up here? Well, wherever I see an x, I will replace it with x plus h. So I get an x plus h squared times y minus 4x plus h to the third y squared. Pause the video and try to figure out how I made this using this formula and got this formula. I'm just plugging in x plus h wherever I saw an x, okay? So, because otherwise we're not going to move. Like, we have to actually move in this direction. And you'll see that because our direction was very simple, I only moved in the first slot. So my y's just stayed the same. I just get a y and a y squared. That's why this is a little easier. That's why partial x is sort of the easiest derivative to take. We're just moving in one of the variables. Okay. Anyway, so here we have this formula, and let's expand it out. Let's do x squared plus 2xh plus h squared. I told you this is going to come up forever and ever. You should just be good at like cubing things that have two terms. X to the third plus 3x squared h plus 3x h squared plus h to the third. Just get really good at that. How? Well, you have Pascal's triangle to help you for those coefficients. You can even go up to taking things to the fourth power. Just learn how to do that, okay? And then I have to get this piece now, minus x squared y. And then I have a minus and a minus, so carefully I'll do a plus. Okay. All right, I'm getting there. Let's see here. Now this y has to come through and hit everything. And this 4 and the y squared have to come through and hit everything. Oh my gosh, too many arrows, so I'm just going to sort of do this. So first I'll do this one. Now I have minus 4, and this is a minus 4 coming through, a minus 4y squared. And maybe even, just to help me out, I'm just going to move the y squared over here. Oh, maybe it needs more room. Okay, so this is getting quite cluttered, but anyway. So now I have a minus 4y squared times each of these 4 terms. Okay, and that'll give me 4 terms, but they'll have more stuff in there. Y squared x to the third minus 12y squared x squared y h, or x squared h, minus 12x y squared h squared minus 4y squared h to the third. And then I have this stuff. And now there's going to be some cancellation. And you should just know that whenever you're doing derivatives, things are going to cancel. So be prepared for it. And now is the moment. Minus x squared y, basically whatever has been waiting in the f of xy, the part that didn't change, the initial, that's going to cancel things. So I need to find an x squared y over here. Sure enough, there it is. I know this is going to cancel something. There needs to be a minus 4x to the third y squared somewhere. And there it is. Those are gone. Okay, and now what will happen every time is that anything that remains we'll have an h. Here this is one h. Here there are two h's. One h, two h's, three h's. And so I'm going to divide, and when you divide like this, it has to come through and hit every term, all 5 terms. What do I have at the end? 2xy plus hy minus 12y squared x squared. The h and the h cancel, so that's a 1. Minus 12xy squared h. The h and the h squared become an h squared. And now there is no more divide by h. I'm done with that. Okay. But now what do I have to do? Limit as h goes to 0. As h goes to 0, all terms with a surviving h will disappear. That means this will go to 0, this will go to 0, and this will certainly go to 0. H squared goes to 0 really fast. And so, what is my answer? 2xy minus 12, and usually we do x before the y, so I'll write this x squared y squared. That's it. That's the answer. Let's check. Did I get the answer that it said I should get? 2xy minus 12x squared y squared. 2xy minus 12x squared y squared. Excellent. Okay. So what did we do here? There's a lot of calculation, but the main thing was trying to translate. We had to know that a partial x means moving in one specific dimension. And in our formulas, that came through because right here became here, and then I can just sort of leave the y's alone in the formula, and only my x variable changed. So, and then when things cancel, then it just gives the right remaining stuff. Now, in practice, this is the reason that you can just do this. You can just look at this and say, partial x, well, x squared becomes 2x. That's how we do the derivative. And so x squared y, if y, we treat y as a constant, because we're not going to move in y at all, then y is just a constant like 5 or 18, and it just sticks around. So that's why the x squared y becomes 2xy. Pause and just see what I'm talking about. I'm just applying single variable calculus, pretending that y is not a variable, it's just a fixed number. And if x is my variable, and x squared becomes 2x. And again, partial x, I look at this and I just see, well really it's a minus 4. And if my y is not a variable but is held constant, 4x to the third becomes 12x squared. And the minus sign and the y squared are just hanging around as constants. So we're discovering here that we can really just take derivatives exactly like in single variable calculus, provided we're moving in the simplest possible direction, namely exactly horizontal, or exactly vertical would also work in the same way. So just very briefly, if I took partial y of this thing, what would that be equal to? Well, partial with respect to y would just leave me an x squared. Partial with respect to y here will give me a 2 will come down. So I'll get a minus 8 x to the third y. Okay. So that will be the rule. We can just use single variable calculus rules. But it's not magic. You can see, and the point of this problem is to really essentially prove this will work every time. So we did the limit definition, and everything worked out exactly as we thought it should if we were just doing single variable calculus. Okay. Excellent. So when you answer this question, you should really have pictures with the right dimensions, and you should have the movement vector, and you should say in words what a partial y means, or a partial z, or a partial theta means we move in the theta dimension only. And then in formulas, you should have all this. You should have where we plug in and be very careful and cancel things, and then let h go to 0, and you get the right answer. Okay. So here's another version of this. So you see sort of right here, I didn't use the actual formula for f yet. But then down, like right at this arrow is where I really applied the actual formula for f, and then I had to start calculating in detail. The same thing happened over here. Up here, I didn't actually use the formula for f yet, and then only down here did I plug in the actual formula for our function f, which could change. Yeah. Okay. Quiz yourself. How much can you do? Start out with this. Here, I'll even help you. Pause the video. How much can you do on your own right now? That is how you study. Put a 30-minute timer. Quiz yourself. When you get stuck, rewatch the video. When you get stuck, go to Perusall and type a thoughtful comment or question. And then when you watch the video and you say, oh, that's what I should have done next, you are not done. Then start again, blank sheet of paper, and try from the beginning. Don't try where you got stuck. Don't try from where you got stuck. Try a completely blank page and quiz yourself again. Okay, so if you study this way, by quizzing yourself, then 1 hour of this, like 1 hour of this sort of active studying, is in my opinion equivalent to like 5 hours of just passively watching the videos. So why do something for 5 hours when you could just do it for 1 hour? Please, 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 quiz yourself. That is the best way to study.